Why is Discrete Fourier Transform, DFT, essential for FFT analysis? Imagine trying to understand a complex song by listening to it in tiny pieces. That's what analyzing signals in electrical engineering is like. The discrete Fourier transform helps us see what's really happening in the frequency world. When signals like sound, radio waves, or sensor data are captured, they are in the time domain. But to understand their behavior, we need to look at their frequency content. The DFT takes a set of samples from the signal and turns them into a list of frequencies, showing us how much of each frequency is present. This is important because it helps us identify noise, interference, or specific signals within a larger waveform. The reason the DFT is so vital is that it provides a clear picture of the signal's frequency makeup. It tells us the amplitude and phase of each frequency component, which is key for many applications. For example, in audio processing, it helps us boost bass or cut treble. In control systems, it helps us see if a system is oscillating or resonating at certain frequencies. Without the DFT, we'd be stuck trying to interpret signals only in the time domain, which makes understanding their true nature difficult. However, calculating the DFT directly from its basic formula involves a lot of calculations, especially when dealing with many samples. This is where the Fast Fourier Transform comes into play. The FFT is an algorithm that computes the DFT much faster. Instead of doing hundreds of thousands of calculations for large datasets, the FFT reduces this to a manageable number. This speed makes real-time analysis possible, which is essential in many electrical engineering tasks. For example, in spectrum analyzers, the FFT quickly shows the frequency components of a signal, helping engineers find problems like noise or interference. In digital signal processing, the FFT allows us to analyze signals quickly and efficiently. It is used in applications like audio equalization, noise reduction, and even in radar systems. The FFT makes it feasible to process large amounts of data in real time, which is critical for modern control systems and communication devices. Without the DFT, we wouldn't have a solid mathematical foundation for frequency analysis. Without the FFT, analyzing large datasets would be too slow and impractical. Together, they form the backbone of how electrical engineers understand and manipulate signals in the digital age. So, the DFT is essential because it defines what we want to know about a signal's frequency content. The FFT is essential because it makes calculating that information fast enough for real-world use. This combination allows engineers to analyze signals efficiently, making it possible to improve systems, troubleshoot issues, and develop new technologies. That's why the DFT is a key part of FFT analysis in electrical engineering.